this is Michelle Ashburner, and we are solving really horribly worded word problems from our textbooks. We are so happy that we bought this very expensive textbook right now. But it is challenging us to think, and so we will take that challenge. This is section 2.4, number 13. So I want you to take a look. You're given this equation. It's P, which is a function of Q, so that's why they write P of Q, and it's equal to 1.2 million divided by Q, and Q is greater than 0. Here's why. P is actually what happens when you want to find out what the actor is charging per the film that they're starring in, and Q is then the number of films the actor stars in. So it's a very interesting relationship where if the actor is starring in 3 films, then they're not going to make quite as much as if they only star in 1. I suppose that their agent goes and sets all this up beforehand, but there you go, a simplified version of Hollywood life. So first we're going to be asked to find Q in terms of P. So here P, if you get a function with respect to Q, so Q is your independent variable, but then it says find Q to be the dependent variable and let P be on the right hand side. And then show that Q equals P inverse, which may seem ludicrous because it kind of almost looks like that, but you do have to show why Q equals P inverse, and then we'll be done. So first thing, find what happens when you rearrange for Q. Solving for Q is easy. If you want, you can just write P is equal to 1.2 million over Q, and then move the Q upstairs to be with the P, so you could start with that step. And then coming to conclusion, you could say, therefore, to isolate Q, which is what we're asked to do, I get Q equals 1.2 million over P. So they kind of mirror each other, these functions do, right? They look like kind of a 1 over x kind of a thing. Whoops, sorry about that. So then it says here that Q is now equal to a function of P. It's a function of P because whenever you put in a P, you get a unique Q out. It's kind of like F equals 1 over x, right? Just said that. And now we have to show that Q is equal to the actual inverse function of P. So that means we have to remind ourselves what it is an inverse function is. So here's that solution with lots of detail, so it's actually not too bad. So Q is equal to P inverse if we can compose the two functions and then get back the independent variable we first plugged in. So this is what I mean. Take the function Q, which is right here. That's the function Q. And then compose it with the function P that we were given originally. I'm not sure if you can see that, but it's right at the top. Then we're going to do that arithmetic and see what we get. So starting with P, we're going to take the function for P and we're going to input that into the function Q. So the function for P is, it's up here, it's 1.2 million divided by Q. It's the original. So I'm going to place that independent variable into Q, and if this starts to get a little confusing, take a pause and just remind yourself at this point that I'm trying to take the function P, composing it with Q, so P actually goes in as if it's the independent variable, and it's not a multiplication, it's just the input. So what do? What does Q do with its input? It puts it on the bottom where we had 1.2 million on the top. So you have 1.2 million on the top and it sticks the input right down on the bottom, which looks absolutely ridiculous, but when you rearrange it by inverting and multiplying, you get 1.2 million times Q over 1.2 million. These constants, of course, cancel and you just get Q back. And you know that then Q is P inverse because you started with Q being the independent variable and then subbed it into P and then subbed the expression for P into the function Q, and then you got spat out just a Q. Now the reason that this is so complicated is because the notation is talking about P as a function as well as P as an independent variable, and same for Q. So the way that we do it with a function f of x and an inverse function f to the negative 1 of x makes it a little easier actually. So part of this was just the wordiness and the strangeness of the question rather than the mathematical difficulty. And that is it for the simplified Hollywood actor's life.